In today's video, we will be going over the utilization of integrals to identify general and particular solutions to a given problem. For our first set of problems, we have been asked to find a function that is a solution of the given differential equation and the given initial conditions. Our first problem is that dy dx is equal to the quantity x minus 4 squared and the initial condition that y of 0 must be equal to 3. We can begin by multiplying both sides by dx, and in addition to that we can go ahead and FOIL the x minus 4 squared, and so we will get dy is equal to x squared minus 8x plus 16, and that whole quantity is multiplied by dx. We can then integrate both sides, the left side with respect to y and the right side with respect to x, and so we will get y is equal to x to the third over 3 minus 4x squared plus 16x plus an unknown constant c. Given that the initial condition of y of 0 must be equal to 3, we can say 3 is equal to 0 to the third power over 3 minus 4 times 0 squared plus 16 times 0 plus c, and so c must be equal to 3. We have therefore found a solution to our first problem, and the equation must be y is equal to x to the third over 3 minus 4x squared plus 16x plus 3. For our next problem, we are given dy over dx is equal to 14x over x squared plus 1. We can first begin by multiplying both sides by dx, and so we have dy is equal to the quantity 14x over x squared plus 1 times dx. In order to integrate both sides of this equation, we will have to use a u substitution where u is equal to x squared plus 1, and so du will be equal to 2x dx. Plugging this substitution into our original integral, we get y is equal to the integral of 7 over u du. Taking the integral of 7 over u, we will get y is equal to 7 times the natural log of u plus c. Plugging in our u substitution, we get y is equal to 7 times the natural log of x squared plus 1 plus c. Given our initial condition that y of 0 must be equal to 7, we can say that 7 is equal to 7 times the natural log of 0 squared plus 1 plus the unknown constant c. 0 squared will be equal to 0 plus 1 is 1. The natural log of 1 is equal to 0, and so 7 times 0 will be 0, and so c must be equal to 7. And so we have found the solution to our differential equation. It must be y is equal to 7 times the natural log of x squared plus 1 plus 7. For our next problem, we are asked to find the position function of a moving particle with the given acceleration function, initial position, and velocity. We can begin by writing out our acceleration function. A of t must be equal to 7t plus 2. Integrating both sides will allow us to find the velocity function because the integral of acceleration is the velocity, and so v of t will be equal to 3.5 t squared plus 2t plus an unknown constant c. Given that we know the initial velocity must be equal to 12, we can plug that into our equation, and so we can say 12 is equal to 3.5 times 0 squared plus 2 times 0 plus c, and so c must be equal to 12. And so our velocity function v of t is equal to 3.5 t squared plus 2t plus 12. In order to find the position function, we now need to take the integral of our velocity function, and so we can say the integral of v of t equal to the integral of 3.5 t squared plus 2t plus 12. The integral of velocity is the position, and so we have x of t is equal to 3.5 divided by 3.0, and so we have 7 over 6 t to the third power plus t squared plus 12t plus an unknown constant c. Because we know that our initial position must be equal to 2, we can say 2 is equal to 7 over 6 times 0 to the third power plus 0 squared plus 12 times 0 plus c, and so we can say that c is equal to 2. And so our position function for this moving particle is x of t is equal to 7 over 6 t to the third power plus t to the second power plus 12 times t plus 2. For the next problem, we are told that a person can successfully throw a javelin on Earth straight up in the air for a maximum height of 400 feet. And they want us to find out if that person threw the same javelin with the same velocity on the moon, where gravity is only 5.3 feet per second squared, how high would it go? In order to solve this problem, we first need to figure out what velocity he threw it with on Earth. We know that the acceleration function on Earth will be equal to negative 32, because gravity on Earth is 32 feet per second squared. We can then integrate both sides of this equation in order to find that the velocity will be equal to negative 32t plus the initial velocity. We can integrate this function once more, so we can say the integral of v of t will be equal to the integral of negative 32t plus v0, and so we get the position function of our javelin, y of t, is equal to negative 16t squared plus v0 times t plus y0. Now we can assume that the person threw the javelin from the ground, and so the y0 term is simply 0. And so we now have two equations, the position function and the velocity function, and two unknowns, time and initial velocity. We know that the velocity at the maximum height of the javelin will be equal to 0, and so we can say 0 is equal to negative 32t plus v0. Solving this equation for t, we find that t is equal to v0 over 32. We can then take this substitution for t and plug it into our position function, and so we get 400, which is the maximum height of the javelin, is equal to negative 16 times our substitution for t, v0 over 32 squared, plus v0 times, once again, our substitution for t, v0 over 32. And so we get 400 is equal to negative 1 over 64 times v0 squared plus 1 over 32 times v0 squared. Solving this equation for v0, we find that it is equal to 160 feet per second. Now we need to redo this process under the circumstances that the javelin is being thrown on the moon. And so our acceleration, a of t, will be equal to negative 5.3, as the gravity on the moon is only 5.3 feet per second squared. Taking the integral of both sides of this equation, we find that the velocity of our javelin on the moon will have the function negative 5.3t plus v0. However, we just solved for v0, and so we can go ahead and say that our velocity function v of t will be equal to negative 5.3t plus 160, assuming that velocity will be equal to 0 at the maximum height of the throw. We can go ahead and say 0 is equal to negative 5.3 times t plus 160 in order to find the time it takes for the javelin to reach its max height. Solving this equation, you should find that t is equal to 30.2 seconds. We can then go ahead and integrate our velocity function in order to find our position function. So we'll take the integral of v of t and the integral of negative 5.3t plus 160. And so we get our position function, y of t, is equal to negative 2.65 t squared plus 160 t plus our initial position, which they're throwing it from the surface of the moon, and so that will just be 0. Plugging in our t for our max height into the position function on the moon, we find that y of t is equal to negative 2.65 times 30.2 squared plus 160 times 30.2. Solving this equation, you should find that your y max height is equal to 2,415 feet. For our last problem, we are told that a basketball player is planning a big entrance into his next game. He is going to jump off a 50-meter high set of rafters with a parachute on his back, such that his acceleration is only 10% of standard Earth acceleration due to gravity. 3 seconds after he jumps, a cannon is going to launch a ball into the air straight at him for a dunk. What velocity does the basketball need to have to reach him at exactly 10 meters above the ground so that he has enough time to make the dunk? Beginning with the acceleration of our player, we have a of t is equal to negative 0.98. This is because standard Earth acceleration due to gravity is 9.8 meters per second squared, and so 10% of that will be 0.98 meters per second squared. Integrating both sides of this function, we find that the velocity of our player, v of t, is going to be equal to negative 0.98 t plus v0. Because our player is jumping off the rafters, for a moment his initial velocity is going to be equal to 0 meters per second. So we can therefore say that the velocity function will just be equal to negative 0.98 t. Integrating both sides of this expression in order to get our position function, we have the integral of v of t, which will be equal to y of t, is equal to negative 0.49 t squared plus his initial position, y of 0. They tell us that he is jumping off of a 50-meter high set of rafters, and so y of t is equal to negative 0.49 t squared plus 50. We then need to find at what time he reaches his height of 10 meters, and so we say y of t is equal to 10, and that is equal to negative 0.49 t squared plus 50. Solving this equation for t, you should find that at a time of 9.0 seconds, our player will be at a height of 10 meters. We now need to ensure that the basketball reaches him at exactly the same time and exactly the same height. We begin by setting up the equation for the acceleration of our basketball. A of t is equal to negative 9.8 meters per second squared. This is because the basketball is on Earth and it does not have a parachute to slow it down. Integration of this equation to find the velocity will give us that the velocity of our basketball, v of t, is equal to negative 9.8 times t plus v0. Remember that we are trying to solve for the initial velocity of the basketball coming out of the cannon, so this will be our unknown. Integrating this equation again to get our position of a basketball function, we have y of t will be equal to negative 4.9 t squared plus our initial velocity times t plus the initial height of our basketball, which is being fired from the ground, and so that will be equal to 0. Once we have our position function, y of t is equal to negative 4.9 t squared plus our unknown quantity velocity times t, we can plug in our known conditions. The basketball must reach him at 10 meters above the ground, and this must be equal to negative 4.9 times t. Now t in our equation for the player was 9.0 seconds, but remember the basketball is not being launched until 3 seconds after he jumps, and so the basketball will have only 6 seconds in order to reach the player, plus our unknown velocity times 6 seconds. Solving for our initial velocity in this equation, you should find that it has a value of 31.07 meters per second. And so the velocity with which our basketball needs to leave the cannon is v of 0 is equal to 31.1 meters per second. That concludes this video on using integrals to identify general and particular solutions to a given problem.